In this video, we're going to do compounds, formulae, and equations. We're going to talk about common ions that you need to remember and memorize, and ones that you can work out but will use. And we'll talk about creating the formulae and doing ionic equations. Now, here in the periodic table is the first step to do this, and you've got to know how to look at the periodic table, most of the groups, and find out what the charge on the ion may be. So in group number 1, which is this group right here, group number 1, you'll lose 1 electron and therefore create a 1 plus ion. Group number 2, you will lose 2 electrons and therefore create a 2 plus ion. Group number 3, you will lose 3 electrons and therefore give a 3 plus ion. We don't do group number 4 because it takes a lot of energy to remove 4 electrons, and if you add 4 electrons they repel each other quite a lot, so that takes a lot of energy to produce, so they're very rare. Next one is group number 5. Group number 5 gains 3 electrons. Remember, they're all doing this to create a full outer shell. Group number 6 gains 2 electrons, and group number 7 gains 1 electron. So therefore, if that is the case, we have 3 minus, 2 minus, and 1 minus. Gaining 3, gaining 2, gaining 1. Now that means you can read the periodic table and go, right, okay, I know what the charge is if I'm given one of these elements within these groups. It does get a bit more complicated when we do redox. Don't worry about that for now. Now, common cations you need to know. Now, what is a cation, first of all? A cation is a positive ion, but often people find it difficult to remember that because there are cations which are positive and anions which are negative. Easiest way, I think, is just to write the word cation and write the word cation with a big plus in for the T. Okay, if you write a big plus in for the T, it reminds you all the time that a cation is a plus, and that means that anion is the opposite, which is negative. Now, ones you need to remember are ammonium, NH4+, silver, Ag+, and zinc, Zn2+. You'll notice that zinc and silver are in the transition metals. So there's very few in the transition metals you have to remember because they are variable in their charges, and we'll talk about later oxidation numbers. Okay, but these are the ones you definitely need to remember. Common anions, these are the negative ions. Okay, hydroxide, OH-, nitrate, NO3-, sulfate, SO4 phosphate, PO4 hydrogen carbonate, HCO3-, carbonate, CO3 and lastly, ethanoate, CH3COOH. Now, this is used mainly in organic later on, and you will use it quite a lot, so don't worry. And a lot of these will be used so many times during your A-levels that you will memorise them quite easily. But the ones you definitely need to know, you definitely need to memorise are OH-, NO3-, SO4 and CO3 You have to memorise those, so make sure that you do that. We're now going to go on to show how you actually do the formula of an ionic compound from the ionic charge. So we've got sodium, and hopefully you've got your periodic table in front of you whilst you're doing this. Okay, always have a data sheet when you're doing your work in chemistry. It's really useful. And if you look at that, sodium is in group number 1. Now sodium is in group number 1, therefore it is an Na 1 plus charge. Chlorine, or the chloride, is in group number 7, so it gains 1 electron, so it's a 1 minus. Now, if that's the case, we know the ions, we got those from the periodic table. All we have to now do, there's 2 methods. One method is to take the numbers and swap them. Okay, so we've taken those numbers and we swap them and bring them down. Okay, swap them and bring them down. Don't worry about the charges themselves. Okay, so forget the charges for now, and then just go Na1 and Cl1. Okay, we've swapped the 2 numbers around. Now, because it's chemistry, okay, we don't write the ones. And also another rule is, if the charges are exactly the same, they cancel out. So basically, charges are exactly the same, and they're 1s, so therefore I just go Na and I go Cl. And my formula is NaCl. Now, another way of doing it is to look at this and go, I need as many ions to cancel out the charge on the other ion. So if you look here, this is 1 plus, A 1 plus will cancel out a 1 minus. You need one of each, and therefore one of each means you will get NaCl. So one of the Na, one of the Cl, and you'll get a neutral overall charge. Okay, so that means two methods, one swapping the numbers, one just looking at the charges and finding out how many ions cancel each other out. And that's our first example of sodium chloride. Our next example is beryllium oxide. Beryllium oxide is a little bit more complicated. Now if we look at it, beryllium is in group number 2, so that means beryllium 2 plus. Okay, we then have the oxygen, which is in group number 6, so that's oxygen 2 minus. We're just going along the periodic table and just doing that. Now, this is more complicated because it's not a 1, but actually in some ways it's more simple. So if you look at this, if you ever have the numbers the same, you don't have to swap them, okay, because they're the same. Okay, also if you look at the charges, and we really should look at it about balancing the charges, you can see the 2 plus balances out the 2 minus. That means we'll need one of each. Okay, so that means the formula is just BeO. Okay, because both charges cancel each other out. Even if we're doing the swapping numbers method, they're both the same number. When they're both the same number, you get rid of them. Okay, so the answer is BeO. The next example involves ions with different charges. So if we look here, magnesium is in group number 2. Okay, and so therefore group number 2, 2 plus. Okay, we then go to the chloride. Chloride is in group number 7. Because it's in group number 7, that means it's Cl1 minus. Now, if we look at this, okay, we can do the swapping numbers method. That means the 2 will go down there and the 1 will go down there. Okay, but I want to encourage you more not to do the swapping numbers, to actually balance the charges. If you're going to be good at chemistry, you've got to learn to balance charges. So if we look here, we can say, right, okay, how many chlorides would we need to balance out the 2 minus? Well, we would need 2 chlorides, because that would then be 2 minus total. That would balance out the Mg, and so therefore the formula of MgCl2, magnesium chloride will be Mg and Cl2. And so I'd encourage you to look at this and look at it in terms of how do I balance that? How do I make this cancel so there's no charge overall? And you have to do that with 2 chlorides and 1 magnesium 2 plus to give MgCl2. So now we're going to go on to use an example which doesn't include 1s. So if we look at aluminium oxide is going to be in group 3, or aluminium is going to be in group 3, which means it's Al3 plus. Oxygen is in group number 6, so we go oxygen 2 minus. Now, again, we can look at this and we can go, let's swap the numbers. So the 3 goes down there, the 2 goes down there. So we get Al2O3. Or we can look at it and look at it in terms of common multiples. So if we look here, 3 divides into 6 and 2 divides into 6. So what we can say is if we try and get to 6, so that's Al3 plus, so that will be 6 plus overall. Okay, and then that means the oxygen would be 3 of those, because 3 would add up to 6 minus, 6 plus, 6 minus, okay, which means we can then write that out as the formula is Al2, okay, and O3. So the formula of aluminium oxide is Al2O3, either by swapping the numbers over or by looking at the common multiple. We're now going to use an example of the polyatomic ions that you're meant to remember and the transition metal ions that you're trying to remember as well. Now, if you remember from when we first started, the zinc is a 2 plus. Okay, and then the nitrate is NO3 minus. Okay, so we've got NO3 minus. So how many of those nitrates do we need to cancel out the 2 plus? Well, we need 2. Okay, so there we have the zinc 2 plus 2 nitrates. That'll be 2 minus overall. That'll cancel that out. which means that our overall formula is going to be Zn. And here's the important thing. You have polyatomic ions here, so polyatomics are the nitrogen and the oxygen, which means that if you have polyatomic ions at any point and you've got multiple polyatomic ions, as in we have 2, then you have to put it in brackets, okay? Okay, so I've put the NO3 in brackets. I know there are 2 of the NO3s, so that then is my small 2. And so my formula is zinc nitrate, or Zn, open brackets, NO3, close bracket, 2. And that's how you use polyatomic ions to make formulas. We're building on to the more complex examples, and these are including the ions that you have to remember. So we've got ammonium, and we've got sulfate. So ammonium, hopefully you remember, is NH4+. And then sulfate is SO4 2-. Okay? So what we look again here, looking at combining these 2 together, and we're saying, right, okay, how many of these do we need to cancel out this? Well, we need 2. So that means NH4+ will need 2 of those. So that formula then means that we have NH4. And again, it's a polyatomic ion, so therefore we need to put that in brackets. Okay, and there are 2 of them. And then we finish it off by putting in the SO4. Okay, so we have ammonium sulfate. So it's important there when we're using polyatomic ions that they're learning to do this bracket around the polyatomic ion, okay, and put the number of how many ions you have, and do it by balancing the charges. We're now moving on to ionic equations and how to draw them. First of all, you need to know the state symbols, and state symbols, S meaning solid, L meaning liquid, and G meaning gas. One of the most frequent ones is actually AQ, which is aqueous. So if it's dissolved in water, and all ionic compounds dissolve in water, so you'll see ionic compounds generally dissolve in water, and all the acids and alkalis will be aqueous as well. Okay, so and remember, dissolved means dissolved to a certain extent. So things can dissolve a little bit or a lot. So when I say dissolved, it's a very kind of vague measure. But generally, if you're doing equations, you should put AQ if there's water around and there's ionic substances. Now, our tips are all acids and alkalis, as I said, will be aqueous. So make sure if you had an acid or an alkali there, it is aqueous. Okay, and the state symbols should be given in the question, so please make use of them. Okay, you'll have it described as to whether it is an aqueous or solid or liquid, depending on whether it's common knowledge. It's really common knowledge. For example, oxygen, you should really know that's a gas. You shouldn't really need to be told that's a gas. Okay, but if there may be a paragraph that may tell you that it's aqueous, or it may tell you it's a solution or things like that. Okay, so make sure you read the question properly. Now, let's put our exam tips down towards the bottom, and you can see here, okay, state symbols, acids and alkalis generally. So what we're going to do with ionic equations is we're going to use the most common one to start off, which is neutralization. Now, it's a chemical reaction in which an acid and a base interact and form a salt. Notice I've put and water. You don't always see water, okay? And that's really important. You don't always see water. Most of the time you will, though. So most of the time you will, but not always. Now, the example we're going to do is the most common example you will come across. So the thing we do first is we split it into ions, and we split it into ions if it is aqueous. Okay, so if it's aqueous, we'll split it up. All right, so what we're going to do, we're going to split HCl up because it's aqueous. So that means we will get H plus aqueous. Okay, and then we go from there and we get plus Cl minus aqueous. Okay, and then we'll follow that on. Okay, plus, and we go for the sodium hydroxide this time. It's aqueous, so we're going to split up the ions. We'll split the ions there, and that means we'll go Na plus aqueous Okay, then we've got the hydroxide, okay, and that is going to be OH minus aqueous, okay. And so we've got our reactants put into ions. And we're going to carry on. I'm going to carry on underneath. I'm going to do the products now. So if I do the products now, I'm going to go to the NaCl. I'm going to split that up, okay, because it's aqueous again, so I'm going to split it up. So it's going to be Na plus aqueous, okay, and then we go from there and we're going to do the Cl, okay, so that would be plus Cl minus aqueous, okay, and then we've got our H2O. Now H2O is a liquid, it's not aqueous, okay, it's not an acid or an alkali, so it stays together, it doesn't split up. We don't split it up into ions. Okay, and there we go. And there we have it. So we've done all our ions, and now we need to find out which ones are the spectator ions. The spectator ions are the ones that don't do anything chemically between the reactants and the products. That means and signs for this is their state doesn't change, or their charge doesn't change. You'll find out later it's really to do with oxidation numbers, and oxidation numbers are usually the same as the charge. I say usually. Okay, so if you look at the charge here, the first thing you look at the Cl minus, you can see the Cl minus aqueous is Cl minus aqueous here. That means it's not doing anything. Because it's not doing anything, I'm going to say that's a spectator ion. I'm going to get rid of it. Okay, so I'm going to get rid of it. We then go to the next one. Okay, let's go to the right this time. Na, because Na, I'm looking at Na plus aqueous, Na plus aqueous. You can see they're both exactly the same, so I'm going to get rid of that. You probably notice at this point there's a colour coding going on here. Okay, the H plus is aqueous here. The H plus has turned into H2O, so it is changed. You can see it's changed state. You can see that it's a plus here. Overall, it's neutral here. Okay, but a really important thing is that this change from an ion is now bonded to make H2O. Okay, so it's definitely changed, so I'm going to keep it in. The H plus has combined with the OH minus, okay, and has then given you H2O. So the OH minus has changed into the H2O. So you notice here I did all my spectator ions in orange, and I did my ions that are in the ionic equation in yellow. So let's just draw out the ones that have changed, which will make our ionic equation. So it'll be H plus aqueous plus OH minus aqueous goes to H2O liquid. And that is our ionic equation for neutralization reactions, where you have an acid and an alkali. So if you have an acid and an alkali, you will get this equation, okay? And it's the most common ionic equation that you come across in both GCSE and A-level. We're going to go now on to do two further neutralization reactions. And the neutralization reaction we're going to do are metal carbonate plus an acid, okay, in this case sodium carbonate, and we're making a salt, and the salt is because the sodium has replaced the H, and remember a salt is when a metal ion has been replaced, a metal ion has replaced a H plus. Sometimes it can be an NH4 plus that can replace the H plus as well. But in this case, it's a metal ion that's replaced the H plus, so there's your salt. We've got carbon dioxide and water. And water indicates it's a neutralization reaction, as well as the fact you've got an acid plus a base. Okay, so let's look at the ions. So the ions are here. We split them all up. We took the aqueous materials and we split them right down the middle of their ions. We're now going to indicate the spectator ions in yellow. Okay, so spectator ions are in yellow, and you can see here that the charge here, the plus, has not changed. Okay, the aqueous has not changed. So we've got aqueous here, we've got aqueous here. Okay, there's no bonding changed or anything like that. We're looking for change to see whether we keep it in the equation. There's no change. Okay. We then look at the NO3. We can see there's nothing changed in there at all. It's exactly the same. So what we can do is we can remove them. But we have the CO3 and the 2H plus. We can see that not only is the AQ changed to a liquid in the water, and we can see the carbonate ion is completely broken apart, okay, and turned into carbon dioxide. So there's a big change going on there, okay? Big change. Now, remember, there's three things we really need to look for. We're looking for that change in terms of the state. Is the state changing? Is the oxidation number changing? Is the bonding changing? Because you can see here it's gone from an ion and it then goes to a covalent compound. A lot of these are indicators about whether you should keep the molecule or the compound in the ionic equation. So if we then take the ions out that of here that we want to keep in the ionic equation, well, you can see that we've got CO3 plus 2H plus goes to CO2 plus H2O, and that's the ionic equation for metal carbonates plus an acid, and it's general for all of them. Okay, let's move on to our next neutralization reaction, and that is a metal oxide plus an acid goes to a salt plus water. Again, water says neutralization, okay? Base plus an acid, because metal oxides are bases, okay? We then put the ions up again, Rb plus, no change in charge. We can see no change in charge. We can see no change in state, it's still AQ. We can see the sulfate, exactly the same, okay? So we get rid of the yellow ones as spectator ions, and that leaves us with O2 minus going to 2H plus going to H2O. If you look here, O2 minus, no longer an ion, it's now covalently bonded, okay, the H plus, covalently bonded, okay, and you see it's changed its state, AQ to L. Okay, so the ones that change, we keep in the ionic equation. So that generally is our three equations that we have for neutralization. For acid plus alkali, and we've got metal carbonate plus an acid, and we've now got metal oxide plus an acid. Now, fourth example is going to be precipitation. Now, first of all, precipitation reactions are where we create a precipitate. A precipitate is when you have liquids, or usually aqueous solutions, that you add together and then they make a solid. So here's our example, lead nitrate, add sodium chloride, makes lead chloride solid. That's our precipitate. Okay, so that's our precipitate. And then we've got our salt over here. So that's why it's a precipitation, because we create this solid. We take the ions, and we can see that the nitrate is staying the same. We can see the sodium is staying the same. We can also see the Pb2 plus has changed from aqueous to solid. So there's the change there. Okay, and we can see the chloride ions have changed from aqueous to solid. Okay, so we keep those in because there is a change. Once we've kept those in, we put out our equation, Pb2 plus 2Cl minus aqueous, PpCl2 solid. And that is our ionic equation for three neutralization reactions and one precipitation reaction.